Hello guys, in this particular video session we are going to be discussing with an important derivation in the kinetic theory of gases. The derivation is the derivation for RMS velocity or root mean squared velocity, which is the mean of the square of the velocities of the particles of that gaseous part of the particles of gas. So the equation is, let's get straight to the point. It's a very simple derivation which involves a lot of tools in our hand. It's important to note that in physics, what's very clear and important is that we must always have the necessary tools with us so as to establish a mathematical interdependence between the varying physical quantities, so as to obtain a clear and a concise and a precise description of the phenomenon. So what we are going to be using now are a number of tools, including diagrams. First of all, we are going to be considering, let me draw a cube up first. So let us consider a cube. Forgive me if it looks like a cuboid, but it is a cube. Let the length of each side be L. Let it possess an area of cross section of capital A. Let us take a particular particle inside, or a number of particles inside as well, and let us resolve their velocities into three components in three directions. So let us have in this particular path, and in this particular path, and this particular path. So what's important is that let us consider this is the x direction, let's consider this is the y direction, and that the above, let's consider this is the z direction and the above as the y direction or the y-axis. So we can have a velocity in this, let's call this Vy, and velocity in the x direction called as Vx, and velocity in this direction called as Vz. Now let's keep one important concept in mind, that as a tool, that V square, which will be the net velocity, let me call as Vn square, will be equal to the vector sum of the squares of the velocities in each and every direction so considered, which can also be written as in equationally as Vx square plus Vy square plus Vz square. Correct. Now, what we'll be doing is start with the derivation pertaining to the pressure exerted by a molecule in the walls of the container. Correct. For that, we need to understand, let us consider a particle, let us say P, moving in the x direction, and let us consider it to be moving in the positive x direction. Now, if it is moving in the positive x direction, and let it possess a specific mass, that is m. Now the momentum which will be possessed by the particular molecule as it moves in the positive x direction will be equal to, that is p in the x direction will be equal to mvx. Now this is when a particle is moving in the x direction. Now if a particular particle, let us consider this to be the wall of the container. If we consider one particular particle to be moving in this direction, at the next instant, this particular particle will move, and when it collides with the wall of the container, the particle now begins to experience in such a fashion that it rebounds back into the medium. This form of collision with the wall of the container is such that we define it as a elastic collision. Why is it elastic collision? First of all, our definition of collision must be clear. Collision doesn't necessarily mean the two particles must actually physically come into contact with each other or collide with each other. What it means is that when the motion of one particle is affected by the motion of the adjacent particle, that event is termed as a collision. For example, when that is what actually takes place when two particles come close to each other. There exists a force of repulsion such that their relative motion gets disturbed. That event is called as a collision, and whatever this particle undergoes is also a collision, because the second criterion is also met. The second criterion is met wherein the momentum possessed by the particle is also conserved. So now coming back to the topic, when the particle is now moving in the negative x direction, the resultant velocity is now thereby in the opposite direction. Correct? So the net velocity in the because it is moving in the opposite direction, let us say minus x, will be equal to mvx. Right? Now we have to consider an important concept where we consider the change in the momentum. Now you must know where I am going towards is pressure. And to know pressure, which is equal to force divided by area, I need force. Force you can say is mass into acceleration, or you can say force is also equal to dp divided by dt, or delta p divided by delta t. That is, rate of change of momentum is defined as force or change of momentum with time. That is what I am finding out over here. So this delta p can also be written as final momentum minus the initial momentum. This final momentum over here is minus mvx and initial momentum is positive mvx. So when I subtract one from the other, I land up with minus mvx, which is now equal to negative 2 mvx. Now, keeping this value as 2 mvx, considering its magnitude, I'll keep this in my toolbox. Diverting your attention towards another basic concept. We know velocity is equal to distance or displacement by time. Not distance, displacement by time. Now what I'll do is, I'll substitute one for the other. Right? I'll take time is equal to distance by velocity. Let's keep this part. At the same time, what is the distance here? See, the distance is nothing but the time, the distance or displacement or distance, we let us consider in this scenario, between two consecutive collisions. Correct? So we have one collision here, and let us say a collision in the other face. So the distance traveled by it is one single L and thereby another single L. So the distance will be L plus L, and that will be 2L. So the V over here will be equal to 2L divided by T. Correct? And the velocity we are talking about is in the x direction. So Vx is equal to 2L divided by T. Okay, so this is not needed. So your time will now be equal to 2L divided by Vx. Now we must note that this T is equal to 2L by Vx. Where are we trying to go? We are ultimately trying to go with delta T. Correct? So this delta T can be written as 12 by delta Vx, you might argue. But what I have actually done is taken an average of the velocity of the particle in the x direction. Correct? Even then it's not necessary. You just differentiate it with respect to the particular time. So 12 divided by Vx, if this be the change, for example. Let us keep this so. Now substituting it in the equation, dp divided by dt. What I get right now is a very simple equation. I have minus 2 mvx, which I consider positive 2 mvx. Right now only the magnitude for 2 mvx and this delta t. Now what I do right now is I divide delta p by delta t to get 2 mvx now divided by 12 by vx, which can be written as 2 mvx into vx divided by 2l. And 2 and 2 gets cancelled. My resultant force is equal to m vx the whole square divided by 2l divided by l. This is the first part of our derivation. Quite simple. Now we move on to the part where we have to find out pressure. But before doing that, we have to take into account that what we have actually done is find out for only one molecule. Our aim is not to disturb this resultant equation, but at the same time adapt it to its n number of molecules. Now let me take my equation where force is now equal to what? M, now Vx the whole square, Vx square divided by L. To consider n number of molecules in the x direction itself, what I shall now do is multiply and divide with n so that I orient my answer towards n number of molecules. So for this can also be written as m into n divided by L, but at the same time I'm not just supposed to write Vx. I'm also going to write it in another form, that is Vx1 plus Vx2. So this is the more appreciated step, the more relevant step to be precise. Vx2 plus Vx3 goes on goes until Vxn the whole square divided by n. What we are actually saying is that we have n number of particles or n number of molecules moving in the x direction, but the magnitude of these velocities with which they are moving in the x direction need not be the same. So what I am doing right now is taking each of these velocities, correct, and I'm adding them up, right, and I'm dividing them with n and squaring them and dividing it with n to get a cumulative average. So what I do right now is that I consider this one particular entity as a sigma j, for example. I divide it with the total number of terms with respect to whatever it is. I assign it a variable, right? So after I do this, what I do is basically treat it as an arithmetic mean. So my force right now becomes equal to m into n divided by L the whole into, what do I write it as? V square the whole power. but this is in the x direction. Now, this is what we have landed up with considering n number of molecules. But at the same time, I told you to remember this particular equation as well. If I didn't, forgive me, remember it now. Vn, this is nothing but the V net to the whole square is equal to Vx square plus Vy square plus Vz square. Now, what happens if I consider the probability for a particular particle to move with a specific velocity in the x direction to be the same as the probability with which the particle will move in the y direction, with the probability with which the velocity with which the particle will move in the y direction will be the same. That is, I right now say that the probability with which the particle will move with a specific velocity in the x direction is the same as the velocity with which it will move in the y direction. That probability will be the same. So what I'll right now do is, if we consider that particular case, there exists very probable chance, and even if they are equal, what I right now do is, I consider Vx square to be equal to Vy square to be equal to Vz square. So I'll take Vx square, Vy square and Vz square, and let me take Vx as the major component, major entity of this particular equation. So my Vn square, taking Vx itself over here, I'll get 3Vx square of just adding Vx plus Vx plus Vx, because this is equal to this, A is equal to B is equal to C is equal to D, and if I add A plus B plus C, that's nothing but A plus A plus A plus A if needed. Coming back, so this will be my resultant equation. Right now, what I've done is, I've already had this, correct? What I shall be doing right now is one more important concept. Is that what's quite important to note is that the probability which we are actually talking about over here is not just with respect to velocity, with respect to the arithmetic mean for this well. That's something which I forgot to include. So if you consider this as well, my resultant Vn square will be of this philosophy. Let my Vn, to avoid some hassle, let I write it in this case itself, and 3Vx squared. And from this, I will move to the part where I shall now write Vx square the whole bar to be equal to 1 by 3 V square the whole bar, which I shall now write force is equal to m into n divided by L the whole into 1 by 3 into V square the whole bar. Now, what I shall be now doing is, then I have obtained force. An important problem has been solved. I just divide this with area to give pressure. So pressure is equal to force divided by area. Correct? Let me write this with a different color. This can be written as m into n divided by L the whole into 1 by 3 V square the whole bar. But there is area. And dimensionally, area can also be written as equal to L square. L into L, right? So I can write it as 1 by L square. Not just dimensionally, area is that. So my resultant pressure, which is equal to force divided by area, will now be equal to m into n divided by L cube into 1 by 3 V square bar. Where at the same time, this L cube which you see over here can be replaced by volume, because L cube is nothing but L into L into L is nothing but volume. Now what I shall do is consider m into V. We have come across this equation where rho, which is the density, is equal to mass by volume, where m is the force and V is the volume. Do not consider this V and that, confuse that V and this V. This V over here is velocity, this V over here is volume. So what I shall now do is that my resultant pressure will now become equivalent, it will be equal to rho into n into 1 by 3 V square bar, or a more familiar form where pressure is equal to 1 by 3 into rho into V square the whole bar into n. But if n is equal to 1, this will be my resultant equation, which you see over here. So now what I've done is followed the first and most important aspect of this question is, what is pressure? I shall now take this equation and derive RMS velocity with it. Now remember, keep it in your mind that RMS velocity is nothing but root mean squared velocity, which is nothing but V square the whole bar, which is what we have been dealing with so far in this particular case, this one which you see. So what I shall now be doing is that I have derived 1 by 3 rho into V square the whole bar. This can also be written as 3p divided by rho, where V square the whole bar is equal to this much. So V square the whole bar, or in other words, let me take V, is equal to whole square root of 3p divided by rho. Correct. Now, by ideal gas equation, I know pressure into volume is equal to N into R into T, where P is pressure, V is volume, N is the number of molecules, R is the ideal gas constant, and T is nothing but the temperature in Kelvin, right? So what I shall now do is make P the subject of this equation, where P will be equal to RT divided by V. Now, in this particular equation, let us confine our discussion for a number of molecules to be equal to 1. So now my pressure will be equal to R into T, where N actually becomes equal to 1. At the same time, my rho will become equal to mass divided by volume. Right? So from this, what we understand is making substituting values over here. V bar is equal to whole square root of 3 into P. I will write it as 3 into RT divided by V into 1 by rho can be written as 1 divided by mass by volume. Correct? If I write this in another form, it can be V volume into mass. Correct? So what I basically do is volume divided by mass. Now what happens is volume and volume gets cancelled. So my resultant V bar is equal to whole square root of 3 RT divided by M. So we have come to the point where we have finished the derivation for equation for the RMS velocity. What we have to understand is the terms which are used here. V bar over here is the RMS velocity. This is the whole square root symbol. 3 is a constant. R is the ideal gas constant. T is the temperature in Kelvin. And M is the molecular mass, because our discussion over here, rho is equal to mass divided by volume. That's our discussion here. So that's how we derive RMS velocity. That equation you see in the end, that's RMS.